Hello everyone! Today we are going to learn how to transform our particles into swarms. If you have seen my work, you already know that I love to develop particle emitters and give them some complex and organic movements. I have done a few works back in 2014 with this swarm movement in processing. With this method, I've done a sound reactive app to use while I was VJing, develop an artificial ecosystem with different animals and plants, and my favorite one is narrative art where my little birds draw an image. Now I have jumped from processing into Houdini and adapted this swarm system into Vex. Just to show you where I started, there is a website that I used when I first started, where they explain in detail how the system works and the three main forces we need to program. The website link is down below on the description. On this tutorial, we are going to work with particles, but instead of using a popnet, we are going to use a simple solver node to control our particles. This node works kinda like processing with the draw function, where we use the previous frame to save our data and animation. So let's jump into Houdini because this tutorial is going to be a big one. Okay, so these two are the main sources we are going to use to develop our swarm system. This is the website by Craig Reynolds that he explains the three main forces we are going to use to develop our swarm system. Separation force, that's avoid crowding, like our bird is going to try and avoid the other birds. Alignment, our bird will follow the same direction as the other birds. And cohesion, our agent or bird is going to try and go to the middle between other agents or birds. And on the left we have my app from processing, and I'm going to use this. So if you come from and already know processing, you are going to know how to transition like I did from processing to Houdini Vex. So let's jump into Houdini before you get afraid. Let's place our geonode, and same as the others, call it particles. Let's place a sphere. This is the main source of our particles. Let's increase the uniform scale to 3. Place a ISO offset just to make it a volume. The uniform sampling, let's go maximum just to have a nice sphere. And then scatter. Why are we using the ISO offset? It's because like this we can create particles inside the sphere. If we do sphere and then scatter, we are going to scatter the points only on the surface of the sphere. So if we place a ISO offset between, we are going to place and scatter our points inside our sphere too. Okay, so before we jump into our solver, like I explained before, we are not going to use popnet. We are going to control these points as particles, but not with popnet. So before we start, we need to give some attributes to our points, right? Like I did here on the processing. We create some variables, some data that we are going to use on our animation. So let's do the same here, and let's place a point triangle. And with Vex we are going to control and give the data we need. So let's start by creating the ones we need. I'm going to press Alt E so we can have a Vex window to program, because we are going to program a lot of code, so I'm going to open a lot of these windows. It's easier than this little one. So we need a velocity, a vector, acceleration vector. This float r is our search radius. In this case I'm using only one. but we are going to use three different search radius, and this search radius is like the distance we are going to look for other particles. So we will have one for separation, one for alignment, and one for cohesion. Then we need a max force, max speed, and we don't need color and trail size. So let's start. So as I said, we need a vector for velocity. Right now we are going to random this velocity, so every particle will have a different velocity at the start. So let's place at random. We're going to use the position times some seed number, random number you want, minus set another v vector, and times by 2. By doing this little function, we are going to give a random velocity between 0 and 1, giving a set minus this vector, and times 2. This is going to give a random velocity between minus 1 and 1. Okay? So we have the velocity. Before we are going to give just an ID to our particles, just using the point number to give the ID. So we need the velocity, we need the acceleration. Right now we are going to create an empty vector, a 0 by 0 by 0 vector. And we need to create the search radius. Let's start by doing that. Search, no, let me give separation radius. It's going to be a channel float. Separation radius. Just to copy paste this. So we have the separation radius, the alignment radius, alignment, yeah, and our cohesion. Sorry for my accent. I hope you understand. So we have our separate radius. Those flows will be the search radius for each force, right? And now we need a max force. Again, we are going to use a channel float. Need a max speed to control the velocity of our particles so they don't go really fast. And that's it for now. Let's just do. We are going back to this node, but for now I just want this. Okay, so if I press this little button, as the other tutorials, we are going to get this. So let's increase, like, this is separation radius, want only 1, 5, and maybe 8. Max force, a small number, and the velocity, let's put 0.5, the max speed. Right now it's not going to work anything because we are not using these vectors for now. Just to be sure they are going to, we created everything. Let's see, position, we have our acceleration, our search radius, our ID, max force, max speed, separation radius, and our velocity. Okay. So right now let's place our solver and dive into this solver. This is where we are going to change the velocity depending on the forces and change our position with that velocity. Okay, so I'm going to try and I'm going to change this little interface. Where can I do that? Okay, I want this one here and close this one. So we'll have more space to work. Okay, so here is our node system. So we have particles, right? So right now we are going to use a lot of point triangles to change our particles. Let's place a point triangle and let's start our system. Right now we are going to do this. I'm going to transition this code into vex. So let's start with the separation. And again press Alt T or right click and then go to expression, edit string to open our nice window. Okay, so we need our source. We have already our search radius, so we are going to need to create a vector and set to 0 by 0 by 0. This is going to be the vector that is going to change our acceleration, and this is the separation vector. Okay, and we need a count. This count for now it's 0, but it's going to tell us how many points, how many other birds are inside our search radius. And only if we have any particle or point inside, if this count is different than 0, that we apply the separation force. Okay. So for now, let's see how many points are inside. So let's place a for loop. This for is going to start with 0. Okay. The max is going to be our number of points, and we are going to increment one by one. So this for loop is going from 0 to n points. What these endpoints means are these endpoints is the number of our scatter points. If we change this to maybe 500, these endpoints will tell our for loop to go from 0 to 500 one by one, like 0, 1, 2, 3, 4, and etc. until you hit 500. But we just need to give a statement just to be sure that the point number we are going to be on, like if you are on the particle number 5, don't do this code, because you are going to get infinite loop, let's say. So if our point number is not the one we are going to evaluate, just skip it. So we have a vector, let's call it other point. We are going to get the position of that point we are going to evaluate. 0. We want the position, right? And the index is to y. Okay? And we need to know the distance between that the point we are going to evaluate and the other point, to see and to know if it is inside the search distance. Okay, so let's place a distance. Our Houdini has already this function, and we want to use the position of this particle and the other point. Let's call it other point position so you don't be confused what we are going to use. Other point position. Okay. So right now, as I explained, we have the distance, and now we need to know if this distance is is less than the search radius. Because if it is higher, we don't care about it because our bird is not seeing the other one. So first, we need to know that the distance is greater than 0, okay, and the distance is less than our float attribute that we created, that is the sep radius. I think I just let me go back and check if this is the sep rad. Okay, sep radius. So we have our statement, right? And let's increment by 1 our count. So this is the thing I was talking about. If this other bird is inside the search radius of our particle, increment our count number, okay? Our counter. So right now, let's place a vector that is the difference between our position minus the other point position. So right now we are going to do these calculations. We need to know the difference between the other point position and our particle position. Let's normalize this vector to have a length of 1. Divide this vector by the distance, so we won't have we have more of smooth vector, okay, and increment this new vector to our separation vector. Okay, so what this is going on, you are going for to a for each particle. Go inside the solver. So each particle are going to get inside this node, and the separation that is going by 0. So imagine you encounter other particle inside the search radius. So you jump on to it, you add the count, and then do this math to have a new vector called difference, diff, and we are going to add this difference to the separation vector. So if imagine we have already one, the next one that is inside the search radius is going to increment that difference to the previous separation vector. It's not always adding the new one to the 0 by 0 by 0. It's going to look always for the previous one. Okay. So this is the for to have this little force. Okay. So right now we have this red arrow, but we need to do some math before. What is going on with my vex? If count, how is this going up? Okay, my vex is trolling me. Let's go back. Try it again. If count, okay, is greater than 0, let's do something. We need to know to normalize, not normalize, but divide the separation vector with our float count. Why is that? Because right now we are adding a lot of vectors to a lot of vectors to our separation, but we need to divide to have like the average separation force, okay, of all the particles inside such radius. So we are going to divide and get the average separation force. Now we need to do a simple math just to control our vector so it won't be that big of a force, okay? So the thing we are going to use, we did this already, get the average from the separation. I'm sorry if some of the variables are in Portuguese, but I hope you understand. So right now we are going to use this. We need to know if the length of our new vector is bigger than 0. It's not, if it has something. We are going to normalize, multiply by the max speed, subtract the velocity because we don't want we want a smooth animation. So that's why we are going to subtract the velocity, because if the particle is going like up and right now it needs to go right, don't just go like a 90 degrees. It will go smoother, like a drag force. Okay, and then we are going to limit our new force by the max force. Okay, so we are just going to use this code, but now in vex. So we don't have a point max, as you see, but we have the length of our sep. If this is bigger than 0, sorry, I'm just going, I was going to jump to the last one. If we have something on our separation vector, let's normalize first. Normalize our separate force, and then multiply by the max speed, right? Max speed, and then subtract our velocity, right? And right now we need to limit our max force, okay? We need to limit, but we don't have this function here on vex, so we need to do the real math. So I'm going to do the same. If like the separation is bigger than the max force, we are going to limit to that value. So in order to do that, just get the length of our separation. If it's bigger than max force, normalize again, to have a length of 1, then multiply by our max force. Okay? And at the end, we need to apply this separation to our velocity. But instead of applying the separation to the velocity, we are going to add the separation into our acceleration value, our vector. Okay, so our acceleration times sep. Okay, press apply. If you close, you'll lose all the code you just created. And this is the start for our separation. The other two forces are going to be really easy. Just alt and drag this node, wire, and let's call it align. Sorry, I can't write right now. Why am I missing the case? Okay. And we are going, the code is almost the same. We are just going to change a few math that we are using. The search is almost the same, but we are going to use another math to do the other force, this one. Okay, the alignment now. Again, Alt E. Let's, instead of separation, let's call it Ali. And right now, let's see. Okay, so the alignment, we need to know the sum velocity of all the particles inside the search radius and then subtract. Okay, so we need a new vector. Vector sum velocity set to 0 by 0 by 0. I'm using all these math, and I know that I need to use these because, as I said, you can read this website and check the projects they have, and they explain how and why we are using these new vectors and desired vectors to control each force. I think it is on Java. That's why I transition really easy to processing, because processing is a Java, but in the simple way. And Vex is almost the same, but it's not. But okay, so we have our for loop to check the search radius, but now we don't want the separation radius, but the alignment radius. Okay, the other point. Okay, we have the other point position, the float, but we don't need this one. Right, we just need to count to know if we have some bird inside, and right now we just need to add the velocity, the sum velocity. And we need now we need the val, because we are working with velocity here of this. Let's just indent that. Okay, so we are adding the velocity and not the position. That's the difference. We are adding the velocity to our sum. So if the count is greater, we are not going to work with this, but we are going to do the same, but for our velocity. Divide by count to get the average. Okay, and now we are going to normalize this new. Let me just copy paste this. Normalize this sum velocity, multiply by our max force, sorry, max speed, and edit our alignment. That is going to be our sum velocity minus the velocity our particle already have. Okay, right now we are editing our alignment force, and we need to do the same thing again. As you see, now it's all the same. We are going to edit our alignment, normalize, multiply by the max speed, subtract the velocity, and limit to the max force. The only difference we are going to use is that instead of being outside the count, I want to be inside. So let me just indent this. Oops. Okay, and then last one. So our code won't be a mess. And let's place an else if the count, if we don't have any bird inside, that's the same. We're going to set the alignment to 0 by 0 by 0, just in case this won't break. And add our alignment force to the accuracy. Okay, just like that. And this is our alignment. Alt drag to copy this node. And let's do the cohesion force. Okay. Again, select this node. And let's change it again. Now for the cohesion. On the cohesion, we want to get the average point between all the birds inside the search radius. Okay. And as you see, we need to have some location. So instead of adding the velocity as we did for the alignment, right now we just want the average point position of all the birds inside the search radius. Okay. So let me see. Sum log, desire, subtract, normalize. Okay. As you see, it's almost all the same. Okay. So again, we're not going to work the alignment. Instead of some velocity, we want the sum position. Other point. Okay, let me see if everything is alright. Point, and of course, we want the radius from the cohesion, the search radius from the cohesion. Here we want the velocity, and instead of this one, we want to add the position. But we already we have already done that. So instead of pointing this here, let's just use this other point position, because we already have done that. So we have the sum position, and let's do the same. Oops. Sorry. So we are going to divide that, normalize this vector, and multiply by the max speed. But I think I'm missing something. Sorry, let me jump to the processing. Oh, right. We divide the count, but we need a desired position. Okay, sorry about that. So, we need a new vector called desired. This one is going to be the sum location minus our particle position. Okay. So we have a new position, and that is the desired one we want. Instead of normalizing the sum, we are going to work now with the desired. Okay. And now our cohesion force is going to be the desired minus the velocity. Okay, so if the length of our cohesion is bigger, now let's just replace these ones, all the same math. Okay, our force are all already done. I have an error here. Desired location, some location, because we call it some position, not some location, as I did on my processing. Okay, so now everything is alright. Just I'm just going to jump back. So in this node we are calculating the separation, so we are getting the difference vector from our search radius, so we are getting this one with this simple math, the vector difference. On the alignment we are working with the velocities because we need to know where are the other particles heading, right? So we are going to get the velocity, the average velocity between them. And on the cohesion, we are going to use the sum position because we want the middle position of every single bird inside the search radius. Right now, our code is not doing anything if I press play because we are changing the acceleration vector but not the velocity and not the position. In order to do that, we are going to place another point triangle and we are going to call it update. As you see on my processing, we call apply force. It's the thing we were doing, and then we are adding the force. Okay, and then we need to edit our acceleration and add to the velocity, and then the velocity, we are adding the velocity to the particle position and then reset the acceleration. Okay, so to do that, let's place a point triangle, update, call apply, update, alt E to open our window, and let's do the math. So we need to change our velocity vector and add the acceleration vector, the new one, after we add all the forces. Okay, okay, so now we need to limit our velocity to the max speed because we have a velocity that imagine it is 0. On next frame it has some we add some accuracy, and each frame you are adding accuracy. If you don't limit the velocity, the particles are going really fast at the end because they are incrementing the velocity each frame. So we are going to limit our velocity just like we did on the max force, but now it's the max speed. If it's greater than max speed, let's normalize. And now multiply by our max speed. Okay, this is like the limit function. And now we need to apply that velocity to our particles. It's just simple as that. We have our position, just increment our velocity. And now we need to reset our our acceleration, because each frame we want our acceleration to be back to 0. Okay, just like I did here. Let me check acceleration. Okay, apply, and if everything is going fine, our particles should be moving. Why are they not moving? Let me check. Okay, they are moving. So we have the beginning of our swarm. As you see, for now our cohesion radius is bigger, so they try to go and do these little swarms. Try to alignment. But now I want to change each force to have different strengths. Okay. So like the separation force is going to be bigger than the other one. So when they are really close, they will try to separate. So in order to do that, I'm going to increase this one again. Let's call it separation force, channel float, separation force. Let's give a force to each different one. Alignment force. The last one, it's the cohesion force. Okay. Apply, and then press again this little button to have it. Like I said, I want the separation to be bigger. Alignment can be 1 and 1. So we need to now to apply these new forces to our particles. It's simple as this. Just when we add our force vector to the acceleration, just multiply by the sep force. That is a float. Just multiply by the corresponding force. On this one, alignment multiply by the alignment force, and on this one just multiply by the cohesion force. So right now, if I press play, when they are really getting together, they try to separate, so we have more organic look. Okay, it's simple as that. But if you see now, our particles are going to the infinite and beyond. And as I did on that previous video for the tutorial, I fixed the particles so they don't leave the bounds. Let's say it like that. Just like on processing and in other tutorials, the previous one I did, we are going to check our borders or our bounds. So if the particles quit that bound, just reset or do a bouncing movement. To reset the particles, like if they quit on the X, just go to the other side. I've already done that in the previous tutorial, so right now I'm going to do a different one. And instead of teleporting the particle to the other side, I'm going to do like this bouncing effect. Okay? So, to do that, I'm going to place another one. I was calling bounce. Wrangle. Point wrangle. And let's check bounce. So, first we need to know the size of our bounce. Let's place a channel float, call it bounce. So we can control the size of our bounce. Okay? And to do the bouncing effect, we are just going to place a statement for each coordinate of the velocity, like the x, y, and z. So if the absolute of our position on x is greater than our bounds that we have already created divided by 0, just multiply the velocity on that coordinate. -1. Okay, on X if it is bigger. I'm just going to explain why I did that. Just a minute. On our Z and now on our Y. So right now we have like a box with this size 40 by 40, 40, 40, 40. What that means is that we are going to create this box like this. Okay? And you will see that our particles are not going to quit that box. I hope you can see this on the video. So why are they quitting? Because I forgot to turn on the check bounce. Silly. Okay. Okay, so now you ask, why are we using the bounds divided by 2? Because our bounds is on the middle, right? It's on the origin. So it's not between -40 and 40, it's between -20 and 20. If I use, maybe I'm going to use 50 by 50 by 50, because like that you can see the number on the grid. So as you see, our bounding box is on between 25 and 25 in all the axes. That's why we are going to divide by 2, because we are going to use the absolute. Even if it is on the like -25, it's going to use the absolute. It's going to check, oh, it's -26, so it's greater. Absolute is 26, it's greater than the alpha of our bounds, so let's multiply by -1, so it's going to invert that velocity to the other direction. This is the basic principle of our swarm system. Right now you can play with a lot of things. You can increase the scatter points. Of course my computer is going to die like this. Let's go to 2500. Just for the tutorial I'm going to go to 800. And now with this point triangle, let's call it init, you can change all the parameters you want. If you want more speed, you can increase the max speed. For example, if you want the particles to be all the way super separated from each other, you can change the forces and play with it. As you see now, we don't have those swarm. They are like trying to get away from each other. See? If you increase the alignment, let me just place like this. Is 8. Like, let me increase the alignment force. You'll see that the particles will try to move to the same direction. See? And as we saw before, if we have the cohesion really strong, let me increase the search radius. Let's give all the same search radius so you can see what is the force doing. So let me increase the cohesion force. They're going to try and be like an attractor, right? They're trying to be everything to the middle. The other parameters I had are more into separation. So I had like a separation radius only at 2 and the cohesion radius to 8, alignment to 5. And the force I want the separation to be bigger. But because they are only going to search really close, they are not going to separate all the way. So they are going to try and do this swarm, but if any particle is going to get really close, they try to separate like birds. Okay, so other things that we can do with this one. Let's play with our velocity, for example. Like on processing, the processing works with 2D, and this app is made for 2D. You can do the same here on Houdini, right? Just like I explained on our first into PopNet tutorial, we can edit the velocity, right? So we can like call the velocity on y-axis, for example. Just in order to explain to you, let's place a vector, limit velocity, and we are going to give like 0, 1, 0, and 1, and multiply our velocity by this limit velocity. So right now I'm killing the y velocity, so every single particle are going to move in the ground, but we are using a sphere, so instead of using a sphere, let's place a grid to have every particle on the same y. Okay, so right now if I press play, if everything's go like I think, it's going to be everything on the floor. Cool, huh? Now you can do a lot of things. You can place a trail. We are not teleporting particles, so instead of preserve original, we can connect as polygons, check off the closed rows, and increase this maybe to 15. Pretty cool. So now you have the particles. You can do a lot of things. Let me just turn off the limit. Just add these brackets. So yeah, so our velocity is going on 3D. We have to, okay, everything is alright. Right now you can like increase this and play with this. Let's like convert to VDB, why not? VDB from particles. It's going to take a while. Just increase this by 0.5. Maybe this 2. Just have a blobby effect. Now let's VDB smooth. I'm just trying something. I don't know if this is going to work. Reshape, I think it's reshape. I'm going to dilate by 4. Oops. I don't know how I created that. Now let's erode by 3. Make this. Okay. And now convert VDB to polygons. So we have a different mesh. Instead of particles, now we have. Let me just play a little of this. Our trails will be like this, and our VDB will be like this. I've prepared a file cache with this same system just to show you the possible animation. So let me try and grab it. Cache trails, cache, VDB cache. Okay. Just to show you the possibility. Just like a volume mesh. I think I have 600 in that animation, so This VDB is like this one. We have our particles with a swarm making a trail of other particles and then converting to VDB, do some reshape. And if you don't want that, you can use the trail system to control your particles, and that's it. I hope you understand that. I think this is easy to understand like this. We have a single wrangle for each force, then update our position, and then check bounds just to control the particles to be inside our bounding box. And I think we cover everything. You can scatter your points depending on the object you want. And that's it. Before we finish our video, I want to thank our patrons for the awesome feedback and support. I'm really happy we have reached our first Patreon goal this month. Hope you enjoyed this video, and if you like this tutorial, don't forget to hit the subscribe button and check our Patreon page. Have a nice day and see you on the next one.